Welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Professor Cesar Uribe, who is the Lewis Owen Assistant Professor in the Department of Electrical and Computer Engineering at Rice University. Something about Cesar: he received his Master of Science degrees in Systems and Control from Delft, University of Technology, and in Applied Mathematics from the University of Illinois at Urbana-Champaign. And also he received the PhD degree in Electrical and Computer Engineering from UIUC in 2018. He was then for a while a postdoctoral associate at Leeds at MIT until 2020. And also we were just chatting about this. He held a visiting professor position at the Moscow Institute of Physics and Technology. His research are around distributed learning and optimization, decentralized control, algorithm analysis, and computational optimal transport. And today's talk is going to be on graphs with finite time consensus and their use in gradient tracking. Personally, I've been following Cesar's research closely in the past couple of years, and I'm very excited to hear more about what he's telling us. So Cesar, without further ado, the stage is yours.
Yeah, thank you, Joel, for the nice introduction and for the invitation to present here in Autonomy Talks. Myself also, I've been follower of all the talks, so it's an honor to be able to present to your audience as well. So I'm gonna go right away into the topic. Again, as the name suggests, there is like two main components into this talk. The first one is the idea of finite time consensus, and the second one is how can we leverage those properties into gradient tracking. So hopefully by the end of this 50 minutes or so, we will be able to at least understand these two main concepts and how to relate to autonomy. And before I start, I want to point out that this is a joint work with my amazing student, Edward. So he's the main lead in this work. So he's the driving force, and then in cooperation with Chin and Bi Cheng from Lehigh and Google, respectively. This is a photo of Edward. So if you see him around, recognize him. He's again, the main guy in this paper, and this is the archive link for the paper for those of you who want to go into the details. Right. So again, this is like the general structure of what I want to talk. I want first to present the idea of finite time consensus, which I believe might be maybe the relatively new thing that many of you have not heard before. Some of you might have heard it as well. And then how can we use that for gradient tracking as well? And again, I'll start with pretty much maybe the same slides that every single Autonomy Talk starts with, which is our favorite optimization problem, empirical risk minimization, where we want to minimize over some space sum of functions. And then depending on your area, each of these FIs represents something different. But the idea is that abstractly, I would say 95, 99% of all of our problems can be summarized into something like this. And it's the number of functions that you have. And specifically in my case, I'm going to be interested in functions, FIs, that can be written in terms of an expectation. So each of these functions is an expectation with respect to some randomness, some random variables I. And the randomness is different for each one of the i's. So this means that we are in the heterogeneous regime in which each of the functions are different and they come from different sources of randomness. And in the distributed setup or the decentralized optimization setup, our main assumption is that even though we want to solve an optimization problem like one here, we have a network of agents, and each of the agents are only able to access information about one of these functions. So we're going to say that each of the component functions, FIs, is local and private to one of the agents I. Again, we assume that the agents somehow can talk to each other and they all want to agree on a single minimizer or on an approximate point that it's or a point that is an approximate minimizer of the sum of functions. We're going to assume also that all of our functions are smooth. Sorry, this should be not possibly here. So just smooth functions, possibly non-convex, and with stochastic oracles. So that's the main difference in the setup that we're going to talk about. So possibly non-convex functions with stochastic oracles, and all of the randomness comes from independent random variables, but each one of them with a different probability space. So that's, again, the general framework of the work that I'm going to present. And now the motivation here, or the idea of this finite time consensus, is sort of, if you may call it, like anti-autonomy talk type of thing, which is many of the driving forces in distributed and decentralized optimizations and the things that have been happening in the field for the last 30 years or so comes from control theory and from autonomy ideas, in which we have a picture like this, right? We have fleets of drones or self-driving cars or robots or you name it, and they are somehow interacting with each other. And the whole point of autonomy is that we don't know, or we cannot model exactly the environment or the dynamics of every single one of them. So we usually, or most of the time, work on this idea of worst case scenarios. So we assume what is the worst case network, communication network that we can handle, what is the most noise we can handle. So in general, this type of distributed systems analysis, and rightfully so, focuses on worst case scenarios, which is what is the worst thing can happen, and are we still resilient and robust against those adversarial conditions? However, most of these ideas of distributed optimization have been absorbed or borrowed by machine learning communities to start studying the idea of distributed computation or distributed machine learning setups, in which now, instead of drones flying around with unreliable communications and environmental disturbances, we have agents representing computational units. And this is the drawing that I have here. The picture is that now our agents are GPUs, TPUs, which are computational units. And what has happened in the machine learning literature is that they have taken one-to-one most of our algorithms from distributed optimization and started like using them for distributed training, because we are robust and resilient, and the setup set us like maps one-to-one to what we want to do. Again, the computing resources are abstracted as agents, and they are connected now on these high bandwidth channels. However, there is a main structural difference, which is in these data centers or distributed machine learning setups, we have fully control of the topology. And this happens to me the first times I talk to people like at Google and Microsoft and all that, and say, yeah, we can handle arbitrary network topologies and we can still guarantee convergence and all that. And then say, like, why would you have adversarial network if I'm the one literally wiring these things into my servers? So then things started to sound a little bit different. And also, communication is very reliable. We're not dealing with unreliable communications in open environments. We're dealing with high speed, highly reliable communication channels between these TPUs that are very close to each other. So the same communication is not a big issue in this case. The type of issues that they face are different. And this is one of the pictures that sort of like convinced me of this. So this is TPU B4. Right now we're in TPU B5 or 6, which is a model for computational units that Google is using. And what they have here, it's inside a single chip. So this is a picture of what's happening inside a single chip. They have a grid of computational units inside a single chip again. And these computational units are connected to each other via highly efficient fiber optic communications inside the chip again. And each of these communication channels can be controlled optically as well at very high speeds. So what we have inside one of these TPU B4s models is that we have a network of computational units talking to each other on flexible but highly reliable communication channels that we can control. Right? So this is a slightly different setup. Right? And again, okay, if you want to do distributed computation on these types of setups, given the structure of the function that we have, remember the function that we have is something like this, minimizing of a sum of functions. Okay, you can say, okay, let's do parallel stochastic gradient descent, where each node takes some samples of the data, computes the gradient, and then they all then you need to do some form of global averaging of all of the nodes. So how do they do that? So usually, like initially what they were thinking or what they're doing was this like parameter server architectures where you have all these agents talking to a single server. They send this information, the server aggregates and sends back the aggregated gradient, so every one of the agents can continue working on full information of the optimization problem. But you can imagine now that if you have this type of architectures where, given that this is a cube, like every time you add one additional layer, you have like cubic growth of the number of computational units. There might be some bottlenecks in the communication if there is a single server that needs to handle all these agents talking to each other at the same time. So the question is, how can we handle this type of communication? So the idea, or what the community in the, let's say, the machine learning community, this parallel computing community solved or proposed is this idea of like ring all reduce type of communications where we avoid this problem where everybody wants to talk to the server at once. So this becomes like a queuing theory and a scheduling problem. So what they usually do in ring all reduce, and this is what Google and Meta and Microsoft and most of these companies do, something like this. So this is just a toy example of 4 agents, and each of the agents have 4 pieces of information labeled 1 through 4. And the objective here is you want to compute the average of all these pieces of information, or you want all the agents to have access to the average of all these 16 pieces of information at some point. So the way this ring all reduce works is as follows. So each of the agents is going to send to the next neighbor the piece of information labeled with its own name. So agent 1 is going to send piece 1 to agent 2. Agent 2 sends piece 2 to agent 3. 3 sends piece 3 to agent 4, and 4 sends piece 4 to agent 1. Right? So, and then the process repeats. Then at some point, every single agent has all the pieces of name 1, all the pieces of name 2, all the pieces of name 3 and 4. But then this is not yet enough. So this process needs to be repeated once more time, such that after these many iterations, everybody has access to all the pieces of information so they can compute average. And this is how this distributed computation is actually built in many companies right now. So you might think, okay, this solves the issue of bottleneck communication because at any given point, you only need to talk to one neighbor at a time. So there is no bottleneck communication here. And then if you compare these two, you'll say, okay, in the first model on parameter server, you have a bandwidth cost of n because the server needs to talk to n agents at once. But then they only need to do that once. So the latency is 1. The latency is 1. So the total cost is n plus 1. And then in the ring all reduce, the bandwidth is 1 because you only need to talk to one neighbor at a time, but then you need to talk n times with your neighbor. So at the end, you get 1 plus n. So even though the cost is the same, let's say for engineering practices, some people might still use parameter server or ring all reduce. But let's say it seems like there is not much improvement in the complexity analysis of these two things. So now the question is, okay, can we do something better? And this is where distributed optimization has focused many years now, which is, can we find some form of different topologies that enable us to do some form of good communication or efficient communication with my neighbors that sort of improves this n plus 1 type of bound that it seems to be there. It's not a bound, but let's say it's do something slightly better. The problem when you change from arbitrary, from parameter server or circular topologies to arbitrary network topologies is that you don't have first of all, you don't have a server that is able to coordinate everything at once. And then you only have access to a partial set of neighbors. So the type of operation or aggregation operation, partial averaging that you need to do is this idea that we have seen a million times where is I'm going to update my estimates as some form of convex combination of the parameters that I'm receiving from my neighbors. And in this case, you can see that this J represents the indices of the neighbors of node I. Right? So WJI simply shows the weight that agent I is given to agent J, and XJ is the information that you're receiving from the node I is receiving from agent J as well. And immediately one sort of like obvious thing that we can see is that, of course, you only need to talk to the degree of the network. So if your network has a degree Dmax, then Dmax is the maximum number of neighbors that a node can have. That's the maximum number of communications that you need to have, right? And then how can you use that into optimization itself? Well, this is this idea of stochastic decentralized or distributed stochastic gradient descent, where you first do local updates. So you move in the direction of your stochastic oracle first, and then you do partial averaging with the information that you receive from your neighbors. So this is sort of like moving in the stochastic, pointing in the direction of your stochastic optimization problem, and then you do aggregation. And then this has been studied many, many times over and over again. The whole idea here is that the communication cost is reduced if your network is sparse. Right? If your network is sparse, then you only need to talk to the degree of your graph instead of n number of nodes. So there is like a little win here, right? Instead of n, you're talking only with the max neighbors. But then is this like all happy, right? So is this free lunch? And the answer is no, because, okay, yes, you gain a little bit, you reduce the number of people that you need to talk at every iteration, but usually you need to pay a price again in the number of iterations that you need to run these algorithms for. And usually this type of dependency this type of price of decentralization depends on the spectral gap. So the connectivity of the graph. So based on if you have a fully connected graphs, of course, there is no price, but then the degree is again n, so you don't win anything. Or you could have very sparsely connected graphs for which the spectral gap is favorable, but then at the same time, then you don't you need to pay a price in a higher number of iterations. So and then in general, this spectral gap depends on the second largest eigenvalue of the topology of the graph Laplacian. So here it's a connectivity measure, right? So for example, for sparsely connected graphs like the line graph or the ring, you have like n squared type of dependency. So the number of iterations, the number of additional iterations that you require for these methods is of the order of n squared. And okay, yeah, so many people have studied this problem over again. That there is this nice summary of results by Angelia in 2018. Again, the per iteration communication cost is Dmax, the degree of your graph. And then at the same time, you have an extra overhead in the number of iterations. So the iteration complexity grows by an order of the spectral gap to the power of 1/3 or so. That's the tightest bound that we have so far. So again, the obvious conclusion is that denser topologies have expensive communication, but faster convergence because this number is going to be small. And sparser topologies has cheaper communication, but slower convergence because this number is going to be large. So again, the question is, can we do better? And this is just an example of a set of common topologies that people use. Grids, rings, stars, and this one is called static exponential graph. Again, this is the analysis. So for example, for the star graph, which is the parameter server, you get n communication, n iteration per iteration complex communications, but then you have an extra overhead of n to the 2/3. For the grid, you have 4 neighbors, but then you pay a price of n to the power of 1/3. Still better, right? It's still, because before we were competing with n plus 1. And then for these static exponential graphs, which are like very nice, almost expander almost expander types of graph. You have log n type of log n neighbors, and the price to pay is again log n 1/3 number of communications. So the question here was, is there some balance or trade-off between these two things that we can exploit? And this is where comes the idea of finite time consensus. But before moving into the result itself that I want to present, I just want to make a small change of notation. So we're used to having first index to start from 1 to n. And here is just for strictly notational simplicity, we change from 0 to n minus 1, but then everything is going to be the same. So if you see starting from 0, don't be afraid, it's just 1. So now this is the definition of finite time consensus, probably like maybe the most important slide for today. You understand this, all is good. So what we're gonna say is that we have a sequences of graphs of length tau. So we have a sequence of graphs of length tau. And we said that this sequence has the property of finite time consensus if once you multiply them together, or a permutation of thereof, you get back the uniform matrix, which is the matrix of all ones by some weight. Why this matrix is important? On the right-hand side of this equality, this is the operation that you use for averaging of your gradients. Right? If you have access to all the gradients of your functions, once you and you stack them in a vector, once you multiply them by this matrix here, that's the same operation as computing averages. But the whole point here is that each of these graphs in this sequence themselves are sparse. So you have a very low degree, and also the fact that I have here an equality. And this is the difference between classical distributed optimization and finite time consensus. This is not approximate. After tau multiplications, we're approximately the matrix of all ones. No, this is exactly. And the question was, can we find sequences of matrices with this wonderful property, which at the same time they're sparse? But then after tau communication rounds, which is equivalent to multiplication of these tau matrices, do we get exactly the consensus matrix, what is called, or the matrix of all ones? Right? This is the definition. And of course, the next question is, are they such a magical set of graphs? Do they exist? Right? And the question, of course, is yes. So some people have studied on this before, and I'm gonna go into it. And again, as everything in machine learning, and I'm gonna stand by this claim, as everything in machine learning was originally developed by control theorists. So, of course, these ideas were developed by control theories by Shreya Sundaram at Purdue, Christos Hagikotsis at Illinois and Cyprus, and Julian Hendricks in Belgium, Kale in KTH. So control theories have been looking into this for a long time now. And here I'm going to talk about 4 examples of this type of graphs. The first one, which I'm going to talk, is this idea of one-pair exponential graphs. Was described in 2021, and which is a type of graphs with this property. And I'm going to talk this a little bit more. And in this case, tau is log n. So you need the sequences are of length log n. But they have a requirement, which is you can only work with graphs whose number of nodes is a power of 2. So you're fine if your graph has 2 nodes, 4 nodes, 8, 16, 32, etc. There is no result for n different than a power of 2. Surprisingly, a couple of years before, this is Mikael Johansson, a KPH, described other type of graphs called hypercubes with the same property, log n, but then you also need to have a power of 2. Again, control theories with Sandro Sampieri and his crowd in 2009 studied these De Bruijn graphs with unique powers of p. Again, you have maximum degree of p minus 1 and log n. And what we're going to focus on our proposal here, this idea of P hypercuboids, which we solve the problem of having finite time consensus for graphs of any arbitrary n. And the main or interesting mathy related result is that the maximum degree is some value of P, which is proportional to the number of prime factors of n. So this is a cute result there, which is what ends up happening is the length of the sequence of graphs that you need is proportional to the prime factorization of the number of agents that you have in your graph. I'm going to talk about this later. So, okay, so let's start with the first one, which is one pure exponential graphs. And then, and before we go in, if you go into the paper, what happens is that all these came from different literatures and the proofs, they were working with different set of assumptions. So we managed to unify all these network classes into a single nice theory of finite time consensus. So one pure exponential graphs, I think it's better to explain it by picture. So this is the case when n equals 8. So if you have 8 nodes, how do you build a sequence of graphs that have this finite time consensus property? Well, n 8 is a power of 2, so the power is 3. So that means that your sequence is of length 3 of log n, and n is 8. And what you do is in the first iteration, this is what I reserve. In the 0th iteration, you talk to your immediate neighbor, so the person that is one hop away from you. The second iteration, you talk to the person that is 2 hops away from you. And the third iteration, you talk to the person that is 4 hops away from you. So this is what I call one pure exponential graph, which is at every iteration, you only talk with one neighbor. And the neighbor that you talk to in the next iteration is a power of 2, right? So it's like a cute way to build these graphs. And the important thing here is this proposition, which is as follows. So if you have n, and then you let tau equal to log n, then the sequences of matrices defined by the, let's say, the one pure exponential procedure, if n is a power of 2, then it satisfies the finite time consensus property. So that's the one, let's say, the first result. So the question is like, okay, can we extend this to arbitrary n that is not a power of 2? And this is where we enter now with this idea of the p-pair hypercuboids. And as the name suggests, p-pair means that I'm going to be talking with p of my peers at every iteration. And the topology of the graph that I'm going to be working with are hypercuboids. And why not hypercube? So imagine that hypercuboid is just like this generalization of a hypercube where the lengths of the hypercube are of different sizes. So a hypercube, all the lengths are the same. So a hypercuboid, every length is different. And foundationally, the type of operations that we're going to, or the idea that we're going to be working with is what is called the base representation of the integers. So I'm going to give an example here. So consider the base 2, 3. And then here I'm representing how do you write the numbers from 0 to 5 in base 2, 3. So number 0 is written as 0, 0, base 2, 3, and number 1 is written as 0, 1. Number 5 is written as 1, 2, 1, 2 in base 2 and 3. So this is just base representation. But the key idea here is that we are going to represent each of the indices of the nodes in the graph in their base representation formed by the prime factors. So I'm going to be going into details here. So what we're going to do is we have n as the number of neighbors, or as the number of agents that we have in our graph, and we're going to find the prime decomposition of n. So n can be written as the product of tau p's, assuming that in this case tau is the number of prime factors, and we're going to represent each of the agents by their base representation. I'll call it like the prime representation. So for example, if I have 12 agents, the prime factorization counting the repeated factors is 2, 2, and 3. So I'm going to write the label or the index of all of my agents in this base 2 to 3 representation. So let's go into some pictures first. So again, this is the example of 12 nodes. So if you have 12 nodes, again, 12 can be written as has a prime factorization of 2, 2, and 3. So that means tau is 3. So there is a sequence of 3 graphs for which you have the finite time consensus properties. But now the question is here, now how do you manage the connectivity between the nodes themselves? So for example, let's focus here between nodes 8 and 11. So nodes 8 and 11, the numbers 8 and 11 in 2 to 3 base representation are 1, 0, 2 and 1, 1, 2 respectively. And I'm only going to connect them with each other if the XOR operation between the base representations at the index where the XOR operation of the base representations are equal to each other or differ. So for example, here, 8 and 11 representation is 1, 0, 2 and 1, 1, 2. So they differ in the second base, right? The first base is 1 and 1. The third base is 2 and 2. So the second one is 0 and 1. So they differ in the second base. So that means that at that iteration, I'm going to connect them with each other. So that's why the G1 is 8 and 11 are connected to each other, whereas in the G0 and G2, they are not. Again, this sounds like a very involved procedure, but if you think about it, this is just an algorithm that can be done very quickly and very easily just by having the base representations and checking their XOR components. So they say the construction of the graph itself is not too complicated. But we get very interesting results. So of course, as we expect, the per iteration communication cost is P. It's the number of the maximum of the prime factors again here. And what we have again, as expected, is that once you multiply all these sequences, all these graph in the sequence, it could be a permutation of them as well. They have the finite time consensus. So, and this is important. So it's finite time consensus, so exact zero error on the consensus computation or the average computation. And then the good thing about working with hypercuboids is that we have the general setup. So again, if we have n to be a power of 2, we get back to one pair hypercuboids, and then we recover back all the results that we are available for hypercubes as well. But there was this thing here of the results of Sanders and Pieri on the De Bruijn graph. So they show that the De Bruijn graphs have also this finite time consensus property. And we were curious about it, like what is this magical thing that is happening with the De Bruijn graphs? That are they something that we have studied before? So an additional result that we have in that paper, by the way, this is how a De Bruijn graph looks like for n equals 8. So if I have 8 agents, this is in general how those graphs look like. What we showed here, maybe this one is the most interesting here, or what we were able to show in that paper is that in fact, the De Bruijn graphs are permutation equivalent to hypercuboids. So this is an interesting result or an interesting connection that we found too. So yes, so this is an additional result there, which is okay. Then that means that pretty much all of the theory that we develop follows or can be written for the De Bruijn graphs as well. The De Bruijn graphs are hypercuboids, permuted hypercubes, if you may. Right. So again, this is try to be like a proof by picture, given that I'm not going into the proofs today. The way we're going to compare the effectiveness of these type of procedures compared to classical methods is that we are going to compare the performance of using finite time consensus graphs with this graph that we call the static graph, which is the union of all the graphs in the sequence. You might think, okay, why if you have a sequences of graphs, why don't you just do the union of all of them, and then it should be better. So what we're going to show is that having them the time varying aspect of the sequences of graphs plays a huge role. And even if you take the union of all the graphs in the sequence of finite time consensus graph, the union of them is not a finite time consensus graph, which is very interesting. Right? So even though you use exactly the same communication channels that you might have used in the time varied sequence, even if you use all of them at once, you will not get the finite time consensus property. So this is the comparison here. And again, here is just like proof by picture. These dotted lines are the error of the consensus error for when you use finite time consensus graphs. So again, the consensus goes to 0 after a finite number of iterations. Here I'm testing, 24 nodes, 32, 36, 72, and 128, 360 nodes, and comparing with the union of all the edges. So it's not that we are cheating here. We're using exactly the same number of communication channels, and yet we still get much faster convergence. But so far, I have only talked about consensus itself. So the next part of the talk in the last 10 minutes or so is how can we use this for the problems of optimization, because at the end of the day, just consensus is not enough. We really want to use this in coordination tasks or in general distributed decentralized optimization problems. Okay, so then how can we handle these type of things? So this is sort of like a summary of let's say what we have so far. So again, if you do a ring type of operation, you need to talk to two of your neighbors at a time, the one in front of you, the one behind you. And then the extra overhead that you pay is n to the power of 2/3. If you do a grid, you talk to 4 neighbors at a time. If you do a static exponential, you talk to log n at a time, but then the price is log 1/3. When we go into the world of finite time consensus, things start to improve a little bit, because 1 peer exponential compared to static exponential, you only talk to 1 neighbor at a time instead of log n. So right away, scalability is much better. And the overhead is exactly the same as before, right? So it seems that we have gained something. It seems that we have gained in the communication complexity, because again, you're not talking with log n, but just with one of your neighbors. With the 1 peer hypercubes, again, you're talking with 1 neighbor at a time, and the price is still log 1/3. P peer hypercube, but again, you remember that 1 peer exponential, they have this challenge, or 1 peer hypercuboids, they have this challenge that you need to have a number of agents that is a power of 2. If you don't have this luxury, then you need to use P peer hypercuboids, where the number of the number of neighbors that you need to talk is the maximum price factor of n, and the communication overhead, interestingly, is the number of prime factors themselves, the power of 1/3, which is like a cool result there. For the De Bruijn graphs, you have p minus 1, and the extra overhead is log n, the power of 1/3 as well. So it seems to be some interesting let's say advantages here in terms of communication and computation as well. So how can we use these for optimization itself? And again, remember from the first slide, the type of problems that I'm interested in are problems that are non-convex and stochastic and distributed. So many people have studied these. So this is an example of the type of bounds or the type of assumptions that we require for this problem class. So one of them is like, it is common, or it is usual to assume some form of heterogeneity or bounded heterogeneity, which is the case where, okay, we're solving a distributed optimization problem, but we're somehow gonna bound how close each of the functions are from each other, and the type of bounds that they have, or the type of assumptions that they have, are usually look something like this. If you look into this, what this bound is telling us is that the gradients of the individual functions, or let's say the variance of the gradients of the individual functions are somehow bounded by the norm of the gradient of the sum of the functions. So this is that these are very close to each other. And you can imagine if all the fi's are equal to each other, then you have a trivial bound. And so this bound is telling us the functions are similar. So this is what is called the heterogeneity bound. And these two constants, P and chi, then gives us the value of this heterogeneity. And one of the interesting results here, or let's say the usual type of results in this area, is that the convergence results usually depends on these heterogeneity bounds. You can see that P appears here in the numerator, and chi hat appears also in the numerator. So if for some reason you don't have bounds, or you have heterogeneous agents, so these bounds are arbitrarily large, your convergence or your computation complexity, iteration complexity is going to be affected by these two numbers. If P is very large and chi hat is very large, you're paying a price based on the decentralization. So the question is, can we remove this assumption? And this is what we started working in finite time consensus as well, which allows us to remove this assumption, and specifically for gradient tracking, because gradient tracking is the type of method that does not require a bounded heterogeneity assumption. So again, the type of setup that we're going to work is we're gonna call our method TVGT, which is time-varying gradient tracking, uses sequences of graphs that come from the finite time consensus property. Each of the nodes can only talk to its neighbors, and Wij is a matrix of weights that have the same sparsity pattern as the graph sequence itself. And the algorithm looks something like this. Maybe I have a nicer form here. So this is classical gradient tracking, just in vector form. So you take gradient steps, you communicate, and then you use the difference of the gradients to track the global gradient of your function. Again, this is nothing new. This is classical gradient tracking algorithm. And many people have studied these gradient tracking methods as well. Again, we consider nonconvex functions with stochastic gradients. And for the case of static topologies, gradient tracking has been studied a lot. So Suleiman and Joan work on this, Anastasia Koloskova work on this as well. And they say we have a good understanding for static topologies. But if we want to use time-varying sequences of graphs, or if we want to use the finite time consensus graph, they itself are time-varying. So none of the theory existing before worked in our case. There's some analysis by Song that studied time-varying topologies for gradient tracking, but the requirement is that they need to be connected at every time step. So even though the graph is changing with time, each of the graphs needs to be connected. And as I shown before, the sequences of graphs that for which the finite consensus property we have been shown, individually, they're not connected. So these analyses do not work. So the second contribution of our paper is precisely showing that, or developing a new analysis that allows for time-varying sequences of possibly non-connected graphs at every time step for the gradient tracking algorithm. So these two are the technical contributions on the optimization side as well. Again, this is how the algorithm looks like. And some of the assumptions are classical assumptions. So we need to have each of our functions to be smooth. So Lipschitz continuity of their gradients. We need to have unbiased gradients. So the expectation of the stochastic gradient with respect to the filtration is exactly the gradient of the function itself. And bounded variance. Again, this is not like extremely strong assumptions. These are the usual assumptions that we need for stochastic optimization type of results or stochastic approximation. And this is, again, the theorem or the result for our case. So if we have those assumptions, just remember that we do not require bounded heterogeneity. If you're careful about the weight or the step size that you're picking, after tau times of running the gradient tracking algorithm with the finite time consensus graph, what we're showing here is a approximate first order stationary points for the non-convex function. So remember, the first term depends how far we are from average. Second term, how far we are from optimality, or for first order optimality. So if you look on the right-hand side, what we have is now first term, which is classical, depends on smoothness and the number of iterations. And the second and third term depends on sigma, which is the variance. So if you have deterministic case, we recover back 1 over t. And in the stochastic case, now you see that the dependency only appears in terms of tau, but in the denominator, right? So this is good itself as a result for convergence. So one of the corollaries, of course, is that if you are careful about the selection of alpha itself, the type of bounds that we have, again, are something like this. And let me go back. So go into these results. Again, the left-hand side of this bound is showing approximate first order stationary point of your non-convex function. And the right-hand side of this bound is showing a dependency on t, which is the number of iterations, L, which is the parameter, and tau, which is the length of the finite time consensus sequence of graphs. So that's the result there. But then if you're working with non-convex functions, especially if your functions are coming from like neural networks and this type of thing, usually the L, which is the smoothness parameters of your function, is very large, right? We know that the landscape of neural networks is usually very non-smooth. So this L could potentially be very large. So another technical contribution that we do here is that if we're careful about the initialization of our algorithm, so some form of warm start, we can improve the dependency on the smoothness parameter. So this is, again, not our techniques. This is not, we didn't invent these techniques, but we adapted them from the ring all reduced case to the final consensus graph, where in summary, if you're careful about initialization, we can reduce the dependency from L cubed to L, which is much better. Right, and you have here L squared, you get L and L. So all the linear dependency on the smoothness parameter, which is a much higher improvement. So again, if you want to compare these two things, existing results do not have smoothness analysis. And in our case, in the worst case, we get logarithmic dependency, logarithmic improvement, but also better analysis with respect to the smoothness constant and the complexity of the network itself. And we also do not require connectivity at every iteration. So it's like a larger number of graphs. So again, how do you compare these two things to each other? Again, this is the type of result. So we get a better dependency on pretty much all of the parameters that we're working with. And just to finalize, I'm going to show again proof by picture on a classical easy non-convex optimization problem with a non-convex regularizer and all these methods. And as is shown here, the methods with the finite time consensus graph, which is the blue and orange lines, have much better performance than the ones with one pure exponential graphs or static graphs. So you actually see an improvement on the number of communication rounds here. Just to conclude, we presented several sequences of graphs that have this property. We particularly focus on the p-pure hypercuboids as a generalization class for many of these graph objects. And we apply them to optimization specifically for gradient tracking by removing some of the assumptions and allowing tighter or better iteration complexity in many of these algorithms. But of course, the obvious question for those of you who were able to follow some of the results is that yes, so all of the p-pure hypercuboid results depends of n being the prime factorization of n, and n is the number of agents, so it depends on how nicely your n is. That's why n being a power of 2 is the usual case, because it's the nicest case. So what if n is a prime? So if the number of, you're just lucky enough that the number of agents in your graph or in your network is a prime. Of course, what is the prime factorization of a prime? It's just one prime factor. So trivially, you get the fully connected graph. The only graph that has finite time property when n is prime is the fully connected graph here. So don't worry about that. So there is this very recent result that we just posted online. I didn't talk about this today, which is how we solve this problem too, which is if n is a prime factor, what is a general or algorithm for generating sequences of sparse graphs, such that after a finite number of them, you get back the matrix of all ones, and this we call this sparse factorization of square of all ones matrices of arbitrary order, because we allow n to be prime as well. But yeah, so this is like the next talk, the next autonomy talk. And yeah, with this, I'm going to finish, and I'll be happy to answer any questions.
Thank you very much, Cesar, for the great talk. Very exciting insights. Also, I love the contextualization with all the other words, and also the puns for machine learning versus control backgrounds. So let's open the stage for questions. You can either unmute and ask or write in the chat, and I can read it for you. I maybe will be the icebreaker. You started with this motivation where you were showing some applications. I was wondering, did you apply some of these very cool technical results to these applications? And if yes, what is the difficulties you found?
Yeah, no, this is the next step. So my student focus a lot on getting the analysis done for the finite time consensus, and what we hope is like for people to start taking these sequences of graphs for which we have many things analyzed already beyond gradient tracking. So one of the, let's say, low-hanging fruits that my student is let's say avoiding is like what happens if you have like strongly convex functions and like slightly nicer function classes, such that you can we improve on those areas too. But in general, that no, we have not yet started looking into like uses for this yet.
Okay, so essentially the hard work was done. Now you have to do the particular cases that might be easy to do, but maybe not.
We don't know, right? So we don't know if it might be easier or harder, because usually like people like for strongly convex cases, like people think, oh yeah, strongly convex is the easy case, and it's not quite, because I mean, yes, it's a nicer function class, but then we're hoping for stronger bounds. So yeah, nicer convergence, but then can you show something stronger like linear rates and this type of thing? So those are usually, or PL condition, this type of things, yeah.
Okay, very cool. So a lot to explore.
Yeah, I see that
So
the question in the chat. Yeah.
Yeah, exactly. Nicola asks, so thanks you for the very nice talk. Did you analyze the finite time consensus behavior when the communications are quantized?
Yeah. This, and I'm sure Nicola was the person to ask me this question, because there has been some works there with the Christos and some people in Europe as well looking into that. And the quick answer is no. Quick answer is no, and the main result is the following. We don't know, we have not analyzed the finite time consensus property with noisy communication, right? If you think of quantization as some form of noise, additive noise, we don't know. We don't know if the properties hold. I'm sure I've seen a couple of papers there in continuous time, but no, we have not done it. Maybe that could be an interesting next thing to look into, which is if we enable quantization, can we still guarantee some of these properties? Yeah.
All right, thank you, Nicola, for the question. Any other question for Cesar? Okay, doesn't seem so, but Cesar left his email. Oh yeah, there you have his email. So in case you have questions for later in the day, under the shower, you come up with some new thoughts. Feel free to reach out to him.
Yeah. Of course, I'll be happy to. Yes, I think the question on what happens if there is a little bit of noise, like the noise accumulation in finite time consensus is not something that we have looked into. That's it. That's an important question from the point of view of autonomy, right? Because, but then again, is we go back, right? The main motivation for this was this highly efficient computational platforms where there is like almost no noise and perfect communication. So maybe we can start like bringing slowly into the real world back again, but we'll see.
Yeah, I mean, but it's nice. There's a lot to explore. I mean, seems that you provide some foundational tools to do so.
Yeah, correct.
Very cool. Thank you again, Cesar, for the great talk. It was great seeing you again. And thank you everyone for attending, and see you all next week for the next talk.
Yeah. Thank you for the invite, and see you.
See you.